Have you ever opened up a control panel door and felt your heart sink as you're met by an array of unfamiliar parts? Once this would have been the problem of the specialist control panel builder, but with the rise of BMS systems in more and more installations, it's becoming increasingly likely that you'll have to get inside one of these at some point. So let's take the fear out of BMS control panels by going on a guided tour of this BMS panel, designed and built by the good folks at Crompton Controls who are supporting this video. Now, because no two BMS control panels are the same, we're going to look at various different components that you might find inside one, even if they're not all present on this one. Depending on the type of panel, it may or may not have one of these, the isolator. This is the device that will prevent anyone getting inside a panel while it's live and accessing any live parts. It will usually sit on the back plate of the panel, where the isolating of the conductors actually takes place. It will then have a long bar that extends to the door of the panel and slots into the isolating handle on the front. The back of the door element of the device is often shaped in such a way that the bar is funneled into the operating handle, as it may have a tendency to drop down a bit. And the arc of the door caused by the hinge means it doesn't exactly line up when opening and closing the front. The operating handle on the front also will have some holes moulded into it so that it can be locked off. Now, you'll find it hard to believe, but some people will intentionally override the isolator by various means, which I won't demonstrate here for safety purposes. They do this so that they can monitor the devices in here, perhaps testing live terminals to see if they're powered up when they should be, or looking at indicating LEDs and readouts. Let us know in the comments if you think that's recklessly dangerous, or if the necessity justifies the risks. Moving on from the isolator, we can then trace the wiring around. These are run through slotted trunking like this, which is cleverly designed to allow cables to enter and exit the trunking through the top during manufacture, and then the lid holds them in place once it's snapped on. The wiring used in this type of construct is usually tri-rated, so called because it complies with three different standards: BS 6231, which is British, UL 758, which is the standard in the US of A, and CSA 22.2 from Canada. It's a fine stranded cable and falls into class 5 under the British standard, and is therefore flexible and perfect for use in a control panel. Depending on the purpose of the panel, the incoming power will generally be distributed to some kind of circuit protection device, usually MCBs. These are used to protect smaller cables feeding various loads either internally or externally to the panel. Very often you'll come across contactors. These come in various guises and types, but will generally have a set of terminals top and bottom that switch various loads on and off. So for a BMS panel, they might control large extraction units and other motors such as water pumps. They turn on and off via signals to these terminals marked A1 and A2. When they become live, they'll change their state and usually connect the supply through the contacts to whatever load they're feeding. I say usually because they can also disconnect the load when powered up, but this is a little rarer. Contactors have the advantage that circuits using large currents and voltages can be controlled by smaller devices with lower voltage and current ratings, like these direct digital controllers, or DDCs, that we'll get to in a moment. Also connected to communicating with the DDCs are the auxiliary contacts on a contactor. Most contactors will have an additional pair of contacts that aren't rated to switch the main loads, but rather are used for signalling purposes. So they might do something as simple as switch on a lamp to show that the contactor is closed and a certain load should be operating, or connect to an input on a DDC to tell the system that the load is operational. It's possible to add additional auxiliary contacts to the side or the top of the contactor to provide additional signalling and control. While we're on the subject of switching loads, you may also come across a similar device that looks like this. This is a relay, which does pretty much the same thing as a contactor, but with a lower current rating on the switching terminals. The relay can be removed and replaced simply by pulling them out of the hardwired base they plug into, making maintenance really easy. You may also come across a couple of other devices in a control panel. One looks like this, and if you paid attention during your science lessons at college, you should recognise it as a transformer. This one is dropping the voltage down for the controls on the panel. Of course, the output from this device will be AC. But if the controls are running on DC, then you might come across something that looks a bit like this instead. This is a power supply unit, or PSU, and it's used to drop the voltage down to the extra low range and rectify it into DC, making it even safer to use for control wiring. Then, somewhere in the panel, you'll usually find a bank of terminals sitting on a piece of DIN rail. These are used to connect the panel to the loads, sensors, and other panels that form the basis of the BMS system. So the connections from the devices inside the panel are brought down to here during the manufacture of the panel in the workshop, and then when they get taken away to be installed on site, the wiring in the building is brought into the panel and connected to the relevant terminal. This makes installation quicker, easier, and reduces the chances that a mistake will be made on site by trying to bring a conductor through the panel and into a component. And now we come to the central component of any BMS control panel, the direct digital controller, or DDC. The ones we're looking at here are part of the Trend IQ5 range from MK Honeywell, and these really are the brains of the whole operation. If the rest of the panel is the body, the muscles, the nerves, the skeleton, then the DDC is the thing doing the thinking, making the decisions and telling everyone else what to do. In other words, it's the brain. So what actually is a DDC? Well, think of it as a smart little computer dedicated solely to managing and optimizing the building's environment. Instead of relying on simple on-off thermostats or time clocks, the DDC takes inputs from all over the building, temperatures, pressures, air quality, flow rates and so forth, and decides how the equipment should respond. Should the heating ramp up? Should the ventilation slow down? Should the air handling unit bring in more fresh air? The DDC works all that out and then sends the appropriate signals back out to the plant. Now, the Trend IQ5 itself is made up of a few key sections. Starting with the inputs, these terminals are where all the sensors land. In a typical installation, you might have temperature sensors, pressure switches, air quality sensors, frost stats, flow switches, basically anything that reports back on what's happening in the building. These inputs can be either digital or analog. Digital inputs are the simple on-off type. A switch is either made or it's not. Analog inputs, on the other hand, take variable readings, so the DDC knows not just that a room is warm, but how warm it actually is. Next up, we've got the outputs. These are the terminals where the DDC sends instructions back out into the world. Again, we've got digital and analog flavours. Digital outputs can turn things on or off, like firing a boiler or switching a fan to run. Analog outputs, meanwhile, can send variable signals, typically 0 to 10 volts, to modulate things like valves or dampers into specific positions. This allows fine control rather than just binary operation. Think of it like using a dimmer instead of a simple light switch. You'll also notice that the IQ5 has a modular design. Some DDCs will have a number of input and output connections built in, but depending on the model and the needs of the installation, you can expand the number of inputs and outputs by adding extra modules to the controller. These simply clip onto the DIN rail and connect via a comms ribbon or bus connector. It means the system can grow as the building's needs change, which is handy when an architect decides halfway through the job that the small office extension actually needs an entire new ventilation plant. Happens more often than you'd think. Now, here's where BMS systems really show their strength, the networking. Each IQ5 controller isn't just sitting there doing its own little job, they all talk to each other. In a full BMS installation, you might have dozens of these controllers spread around the building, all linked together over a communication network. One controller might detect that the return air temperature is rising, another might be modulating valve positions, and yet another might be adjusting fan speeds, all based on shared data and a central strategy. At the top of this hierarchy, you'll typically find the graphical interface that engineers and facility managers use to monitor the whole building. It pulls data from every controller, logs temperatures and events, allows scheduling, and lets you adjust set points without having to physically open up every panel on site. That's especially useful when the panel is in a plant room at the far end of the building that nobody's visited since the mid-90s. So that's what might greet you when you open up a control panel. Hopefully it's taken some of the fear out of that process. This video is just one in a series on BMS that forms part of a training package to help you with your CPD. If you're watching on our training platform, then answer the multiple choice questions that follow and move on to the next video. If you're watching on one of our social media channels, then click the link to move over to the free training package and get yourself a certificate. Or you can watch the same video in the series either right here or at the link in the description to find out how to read a BMS wiring diagram. All that remains in this video is to say thank you very much for watching.